So this is the next sum that we will be solving in our question series on SFD and BMD. So the first thing that we have to do is that we have to start with drawing the diagram as it is shown here, right? So we will draw the diagram. First of all, draw this horizontal line, right? Now what we have to do over here, see at point A, what is the case? At point A, there is a hinge joint. So there will be RAX and RAY. So over here, this is RAY, and over here there is RAX. Then after that, over here, what do we have? We have a uniformly distributed load, right? This is a uniformly distributed load of what? 8 kilonewton per meter. Then at point C, what do we have? We have a force which is at an angle. This is at what? This is at 20 kilonewton. And it is at what? It is at an angle of 60 degree. And over here, we additionally also have an anticlockwise moment of 10 kilonewton meter. Then at D, we will have only a reaction force here, just a vertical reaction force because it is a roller joint. And here we have a clockwise moment of 4 kilonewton meter. And then again we have a force at an angle, right? 12 kilonewton at an angle of 45 degree, right? So this is the diagram that we have right now. So now we have to draw all our diagrams below this. What have they asked us to draw? They have asked us to draw axial force diagram, shear force diagram, and bending moment diagram, right? So first thing that I am doing is I am drawing all these points. I am just drawing this straight lines downward from all the important points. So from here also, right? From D also, I will be drawing this. And from E. Right? So I have drawn all these points. The next step that we have to draw is we have to draw the simple force diagram, right? So here we will draw the simple force diagram. So here there will be a vertical force, horizontal force. Here there is a uniformly distributed load, 8 kilonewton per meter. Here anti-clockwise, 10 kilonewton meter. Now this 20 kilonewton will be divided into its vertical component and horizontal component. So this will be its vertical component, which will be what? 20 sine 60, and the horizontal component, which will be 20 cos 60. Here again there will be reaction at D. Here a moment of 4 kilonewton meter. Here there will be 12 sine 45. And here there will be 12 cos 45, right? So all this has been drawn. Now what we have to do, we have to calculate the values of these unknown forces, right? RAY, RAX and RD, right? So we can do summation Fx is equal to 0. So summation Fx is equal to 0. What are the forces in x direction? First of all, there is RAX, which is in positive direction. Then we have negative 20 cos 60, and then we have positive 12 cos 45, and all this is equal to 0. So RAX will be what? RAX will be 20 cos 60 minus 12 cos 45. Okay, so let us do this. 20 cos 60 minus 12 cos 45. It comes out to be 1.515 kilonewton. Then we can do summation Fy is equal to 0. What are the forces in y direction? Ray is positive minus that uniformly distributed load of 8 into 5. Again there is negative 20 sine 60. Then we have plus RD, and then we have minus 12 sine 45, and all this is equal to 0, right? So we can put RAY plus RD is equal to 40 plus 20 sine 60, which comes out to be 17.32, plus 12 sine 45, which comes out to be 8.49, right? And all this is now equal to 40 plus 17.32 plus 8.49, 65.81. So RAY plus RD comes out to 65.81 kilonewton. So this will become our equation number 1. Now what we can do? We can do summation MA, right? So summation MA is equal to 0, right? In this case, what are the moments about the point A? First of all, there is that uniformly distributed load. So it will be 8 into 5 into 2.5, right? 8 into 5, because this is 5-meter length, and it will, if we are considering it as a point load, it will act at the center. So 8 into 5 into 2.5. Then we will have C. At point C, what do we have? We have an anti-clockwise moment. Now, so anti-clockwise is positive. So plus 10. Then we will have minus 20 sine 60 into what is the distance? 5 plus 2, 7. So this will be 7. Then what do we have? We have this 4 kilonewton meter in clockwise direction. So that will be minus 4. Then we have RD in, which is rotating in anti-clockwise direction. So plus RD into what is the distance? RD 10 into 10, and then minus 12 sine 45 into 30, right? 12 sine 45 into 30. So we have put all these forces together, and this will be equal to 0. From this we can calculate the value of RD. So it will be like, sorry, I have to keep this space free because we have to draw the SFD BMD AFD. So it will be 10 RD is equal to 8 into 5 into 2.5, which is 100, minus 10 plus 20 into sine 60 into 7, which is coming out to be 121.24, plus 4 plus 12 into sine 45 into 13, which is coming out to be 110.3, right? So 10 RD comes out to be 100 minus 10 plus 121.24 plus 4 plus 110.3, which is 325.54, right? 100 minus 10, right? So what will be the value of RD? RD will be 325.54 divided by 10, which is 32.55 kilonewton, right? So we now know the value of RD. We can substitute it in this equation and get the value of RA. So RAY will be 65.81 minus 32.55, which is coming out to be 65.81 minus 32.55, 33.26, right? 33.26 kilonewton. So this is the value of RAY. Now we can put all these values over here. So RAY is 33.26, 33.26. Sorry, that is RX. Sorry, here will be 33.26 RAY. For RAX, it will be 1.515. Then over here, RD will be what? We can rub RD, and sorry, I rubbed it a bit extra, and value of RD will be 32.55. right? Now using this, we can draw all our force diagrams. The first thing that we have to draw is the axial force diagram. So what are the forces in the axial force diagram? All the horizontal forces. We consider all the horizontal forces in the axial force diagram. So the first horizontal force is what? See, at A itself, we have this 1.515, right, in the right direction. So that will be 1.515. So I will do the calculations over here. I will just copy this so that I can use it. I'm just copying this much, right? Control C. I'll just put it over here so we can do the further calculations, right? I think I have missed a lot in that. Just 1 minute. Right? Yes. Control C. And then I will just paste it over here and we can do our further calculation, right? So this is done. So see over here, what all do we have? See, if you consider before, just we will consider the horizontal forces, okay? So axial force to the left of A is 0. There are no forces to the left of A. If we go just to the right of A, we will have one force, right? If we are taking all the forces to the left of this line, we will have this 1.515. This will be 1.515, right? Then at this point B, there is no change. At point C, see, at point B, there will be no change before or after, right? So it will be just 1.515. When we reach C, to the left of C, it is 1.515. But to the right of C, we have what? It is 1.515 minus 20 cos 60. So we will do minus 20 cos 60, which is 10. So this comes out to be, it is minus 8.485. Now this will continue, right? At D also there is no horizontal force. So axial force at D will also be this only, minus 8.485. Axial force to the left of E will be minus 8.485. But axial force to the right of E will be what? Minus 8.485 plus 12 cos 45. Right? So it will be plus 12 cos 45, which is coming out to be very, very small. So it is approximately equal to 0. It is coming 2.8 into 10 raised to minus 4. Right? That is going to be there because we are doing approximation, sine 45 cos 45. So it is approximately equal to 0. So at A, it is going from 0 to 1.515. Right? At A, it is going from, I will draw this in red color. Right? The maximum value is 8.485. So we can take 2 centimeter as 4 centimeter as 4 lines. So this will be 0 to 1.515. Then what is happening at C? It is going from 1.515 to minus 8.485. At C, it is going from 1.515 to minus 8.485. And then again at E, it is going from minus 8.485 to 0. So from minus 8.485 to 0. Right? So just join them with straight lines. Always remember, you have to join axial force diagram with straight lines. So this will be positive, this will be negative. This is your axial force diagram. Now similar to our axial force diagram, we can also draw shear force diagram. Right? In shear force diagram, we will be considering only the horizontal forces. Right? Only the forces in the horizontal direction, no vertical direction forces. So now again we can go down. Okay, what I am going to do, I am just going to again copy this much part. Okay, I will mostly have it in my clipboard, so I'll just paste it. Right, so I have this. I am just doing this so I can see it while doing calculations, right? So axial shear force diagram, to the left of A is 0. Shear force diagram, to the right of A is what? 33.26, right? Then shear force diagram, next point is over here, B. To the left of B is what? Shear force diagram to the left of B is what? 33.26 minus 8 into 5, right? 8 kilonewton per meter into 5 meters. Now it is a uniformly distributed load. So it comes out to be 33.26 minus 40, which is minus 6.74. Now at B, there is no point load, right? There is no point load at B. So shear force to the right of B will also be minus 6.74, right? Shear force to the left of C will also be minus 6.74, and shear force to the right of C will be what? Minus 6.74 minus 20 sine 60, which is what? 20 sine 60 is 17.32. So this will be the shear force at right of C. So this comes out to be 24.06. Right, these are our shear forces for C. Then for shear force to the left of D will be same, no force till there. And then shear force to the right of D will be what? Minus 24.06 plus 32.55, which is coming out to be 8.49, right? And finally we will consider to the left and right of E. Shear force to the left of E will be same, 8.49, and shear force to the right of E will be this 8.49 minus 12 cos 45, minus 12 cos 45, which is what? 12 cos 45, which is coming out to be 0, approximately 0, right? So this is our shear force diagram value. So we can, what is the maximum value in all of this? 33.26. So we can say one line is equal to, let us say, 10 kilonewtons. So one line is 10 kilonewtons, so 4 lines will be 40 kilonewtons. Okay, so we will take this, and here we can mark 10, 20, 30, 40, minus 10, minus 20, minus 30, minus 40. Okay, minus 40, 40. So at A it is going from what? It is going from 0 to 33.26. At A it is going from, sorry, I will just check. Yes, at A 0 to no, it at A 0 to 33.26. So somewhere between 30 and 40 over here. At A it is going from 0 to 33.26. Then at B what is happening? It is staying at minus 6.74. So somewhere over here. At C what is happening? From minus 6.74 to minus 24. So minus 6.74 to minus 24, right? At D what is happening? It is at from minus 24.06 to 8.49. So from minus 24.06 to 8.49, this is D. And at E what is happening? At E it is going from 8.49 to 0. It is going from 8.49 to 0, right? Now how to connect it? What is happening between A and B? Between A and B there is a uniformly distributed load, so it will be an inclined line, right? For a uniformly distributed load in shear diagram, it is an inclined line. From B to C there is no force in between, so horizontal line. From C to D again no force in between, so horizontal line. From D to E no force in between, so a horizontal line. So this is the diagram that we are getting for our SFD, right? Shear force diagram. So we can mark these regions as positive, positive and negative. What is the next thing that we have to do? Next thing we have to do is draw the bending moment diagram. Okay, so to calculate bending moments, what all we have to do? Remember, at wherever there are moments present, like for example at this point C and point D, we will have to take two bending moment calculations, and for other points we will have to do single bending moment calculation, right? So I will do those calculations over here. So bending moment at A will be what? There are no forces to the left of A, so this will be 0. Then bending moment at B will be what? Bending moment at B will be, considering the uniformly distributed load and the point load at A, we will have plus 33.26 into 5 minus 8 into 5 into 2.5, right? So what is the value that is coming? Let us check. 33.26 into 5 minus 8 into 5 into 2.5, which is coming out to be 66.3. Okay, so we can put this as 66, sorry, we can put this as 66.3 kilonewton meter. Then what is the bending moment at C? Again, see, at C there is a moment over here, right? So we have to do two calculations, to the left of C, to the right of C. So to the left of C, what are the forces that we will consider? Plus 33.26 into what is the distance between B and C? 5 plus 2, total distance is 7. So 33.26 into 7, then minus 8 into 5 into what is the distance? This will be 2.5 plus 2, so it will be 4.5. So into 4.5, and no force at B, so no worries. So this is coming out to be 33.26 into 7 minus 8 into 5 into 4.5, which is 52.82, right? 52.82 kilonewton meter, right? Next, we will also have to calculate bending moment to the right of C. Why do we have to calculate to the right of C also? Because there is a bending moment here also. This is what? This is anti-clockwise. See, what is it going to do? It is going to push the left part downwards. So it is going to do hogging, which is negative. So we'll have to subtract 10 kilonewton meter from whatever we have at left. So it will be 52.82 minus 10, which will be what? 42.82 kilonewton meter, right? Then we can find out bending moment. Again at D, we have to do two calculations, to the left, to the right. Okay, there is a simple way to do this. We can just consider the forces to the right, okay, but I don't recommend it. I prefer going from the left only. Okay, so it will be plus 33.26 into 10, then it will be minus 8 into 5 into 7.5, then it will be that will be minus 20 sine 60 is, okay, I will just write 20 sine 60, 20 sine 60 into 3, then there is also the minus 10, right? That is all. So the value comes out to be 33.26 into 10 minus 8 into 5 into 7.5 minus 20 sine 60 into 3 minus 10. Answer is coming out to be minus 29.36. Okay, so it is minus 29.36 kilonewton meter. And bending moment to the right of D will be what? This minus 29.36. And what is this in clockwise direction? So it is trying to push this upward, so sagging, so plus 4. It will be plus 4. So it will be minus 25.36 kilonewton meter, and bending moment at E will be 0 as always. Okay, so we know bending moments also. So bending moment, what is the biggest bending moment we have? 66.3, right? So let us say 4 lines is equal to 60, right? So it will be what? 15, 30, 45, 60. Minus 15, minus 30, minus 45, minus 60. So at A, what is happening? 0. So at A it is 0. At B, what is happening? It is 66.3. So 15, 30, 45, 60. So somewhere over here approximately, right? Okay, I will just come to that. At C, what is happening? It is going from 52.82 to 42.82. It is going from 52.82 to 42.82 at C. At D, what is happening? At D, it is going from minus 29.36 to minus 25.36. So it will be something like here minus 29.36 to minus 25.36, right? And at E, what is happening? At E, it is 0. So between A and B, it has to be a parabolic curve because there is a uniformly distributed load between A and B. From B to C, it will be a inclined line, right? So it will be B to C will be an inclined line to 52.82. 52.82. From 42.82, we are going to what? We are going to negative 29.36. So from here to here, from negative 25.36 to here. So this is negative 29.36, negative 25.36 is equal to 0, and 50, what is before? So 66.3. Here we have 66.3. Now here there will be a parabolic curve, right? But where will the maximum value of parabolic curve will be? The maximum value of bending moment is when? The maximum value of bending moment is when the shear force is 0. So we have to find out the position of this, right? How can we find out the position of this? There are two ways of finding out this position. I have shown you one in the lecture where we can take the equation of the line. Here I will show you a different method which is similar to your bending moment method. Here what we will do, we will say that shear force at this point is 0, right? So what are the forces to the left of this? Okay, I will come over here. That point will be somewhere over here. So what is the location? We can say that this is X, right? We have to do shear force is equal to 0, no? Because here where shear force is equal to 0, their bending moment is maximum. So what we can do over here, see what we can say shear force at X is equal to, what are the forces to the left? First of all, there is positive 33.26 minus 8 into X, right? Because this is in the first, between the first two things itself, A and B. That is why this method will be very easy. And this is equal to 0, right? There are no other forces to the left of this XX, right? There are only two things. One, point load of 33.26 in upward direction, and second, a uniformly distributed load of 8 kilonewton per meter in downward direction. Just putting that, we will get 8x is equal to 33.26. So x is equal to 33.26 divided by 8, which is 33.26 divided by 8, which is 4.16 meter. So we can find out bending moment at 4.16, right? What is the bending moment at 4.16? Again, only two loads. First of all, positive 33.26 into 4.16 and minus 8 into 4.16 into 4.16 divided by 2, it's 2.08. This is for the point load and this is for the uniformly distributed load, right? And that comes out to be 33.26 into 4.16 minus 8 into 4.16 into 2.08, which is coming out to be 69.14 kilonewton meters. So this is the maximum value of the bending moment, which is what? 69.14. So it will be somewhere over here 69.14. So the curve will look like this. Okay, this will be positive, this will be negative, and this is your bending moment diagram. 69 point something, and this is 4 point something. What are those values? 4.16 and 69.14. 4.16 and 69.14. So see, this sum was very big. It took a lot of time to solve, but similar kind of sums will be coming in the exam. So you should try solving such kind of sums.